Good morning, everyone. This is week 1, lecture 5, optimization, utility maximization, and profit maximization. In this particular lecture, we are going to um, look at different optimization techniques, um, how we also try to use constraints to obtain the optimal values. We are also going to look at the concept of profit maximization, and we try to obtain the optimal values for the quantity as well as the price. That is the profit maximizing level of output of the farm and the profit maximizing level of price. So we're going to obtain also the profit function. So as a matter of fact here, we are going to look at the concept of relative minima as well as relative maximum. What relative minima is and then what relative maximum is. And straight away, we then move on to the concept of cost minimization as well as profit maximization. Now, the crux of what we're going to be discussing in this particular course is optimization. How firms as well as consumers try to obtain the optimal values, optimal consumption levels from different sets of bundles, and then how the firm tries to maximize profits um, given these unlimited resources. We're also trying to look at how the firm tries to minimize cost. So let's go ahead and get started. Now, the primary goal of optimization is to obtain the best alternative. We want to obtain the best alternative from a given set of alternatives, considering any possible restrictions on the choices. For example, you have a consumer who would like to know how much of clothing and food she needs to buy in order to maximize her utility or maximize her satisfaction. Again, in the production of a good, we also want to know um, a farm would like to know, for example, the optimal inputs needed in the production process in order to maximize profits or maximize output. So in each of these cases, we use the concept of derivatives with some specified criterion to obtain the optimal values. Now, in optimization here, we're going to have what is referred to as a necessary condition or the first order condition for optimization, which is just the first derivative of that particular function of the profit function or maybe the utility function. So we are going to obtain the first derivative of the profit function, and that is the necessary condition for maximization. And then we're going to obtain the second derivative for the second derivative of the profit function, and that is referred to as the sufficient condition. So there are two main conditions here. The necessary condition. So for maximization, for profit maximization, two conditions need to be satisfied. That is the first order condition or necessary condition, which says that the first derivative is 0, and the sufficient condition or the second order condition, which says that the second derivative must be negative. The second derivative must be negative. That is d squared pi, g squared is less than 0. So, for a cost minimization, there are also two conditions. The first condition is that the first order derivative is 0, the CDQ is 0, and d squared C, the Q square, must be greater than 0. So this d squared C, the Q square, is positive. So we're going to deal with this one when we look at relative minima and relative maxima. And then we try to see the point where the point of inflection is. Okay, so we're also going to look at the concept of utility maximization as well. Now, so this brings us to the concept of unconstrained optimization. So in unconstrained optimization, this one is used when a decision maker seeks to make the best choice from a set of alternatives with zero restrictions on the choices. So for unconstrained optimization, there are no restrictions on the choices that the decision maker is going to make. For instance, a perfectly competitive firm trying to maximize profits. So in an unconstrained optimization problem, we consider a firm seeking to maximize profit, which are defined as the difference between revenue and cost. The unconstrained optimization problem is that the firm must choose an output level that will maximize its profits. So there are no restrictions here, no constraints. So we have the objective function. As a matter of fact, for unconstrained optimization problem, all we need to do is to differentiate the objective function. And the objective function here is to maximize profit. So there are no sets of constraints here. So this is what we're going to do under profit maximization. So you have to note this one. For unconstrained optimization, there are no restrictions on the choices that the individual economic agent is making. There are no constraints on the choices he or she makes. Now, unconstrained optimization problem and profit maximization output of the firm. So how do we obtain that one? Now, in order to obtain the profit maximizing level of output of the firm, what we need to do is to obtain the maximum price at which the firm sells its product. Obtain the maximum price at which the firm sells its product, and which is always the inverse demand function. And this is represented as what? R of Q equals Q times D inverse Q. Now, why do we need to obtain the inverse demand function? Why do we need to do that? Now, the reason is that the firm seeks to maximize profits, and the only way it's going to maximize profits is by selling its product at the maximum price. And how do we obtain that maximum price? We can only obtain that maximum price if we transform the direct demand function to an indirect function, an inverse function. The inverse function here expresses the price as a function of the quantity. So that price expressed as a function of the quantity becomes the maximum price that the firm is going to sell its product. Since the aim of the firm is to maximize profits and minimize cost, so the firm is always going to sell its products at the maximum price. And that maximum price here is referred to as the inverse demand function. So if we multiply the inverse demand function by the quantity Q, then we're going to get the revenue here. And the inverse demand function, which is the price, multiplied by the quantity gives the revenue. Price multiplied by quantity gives the revenue. So a profit maximizing firm is never going to sell its product at the minimum price. You always aim to sell its product at the maximum price so as to maximize profit. And that maximum price is the inverse demand function, which expresses price as a function of the quantity. So if we multiply that price by the quantity, we are going to obtain the revenue of the firm, the revenue of the profit maximizing firm. So the firm therefore maximizes its profits, the difference between the revenue and the cost. That is to say, the greatest difference. It maximizes profit at a point where the difference between the revenue and the cost is the greatest. The profit maximizing level of firm is obtained by taking the derivative of the profit function with respect to quantity and equating that to 0. So equating that to 0 becomes the first order derivative, and that is the necessary condition for profit maximization. As I said earlier, there are two conditions for profit maximization. You have one, the necessary condition for profit maximization, which is the first order derivative, d pi dq, is equals to 0. And then the second order derivative, d square pi dq square, is less than 0. That is to say, the second order derivative is less than 0, or it is referred to as the sufficient condition for profit maximization. So this is the condition that we use to obtain the profit maximizing level of output. If we confirm that profits are maximized via the second order derivative, then we can go ahead and obtain the profit maximizing level of output. So I hope you guys are getting this point clear. Why do we transform the direct demand function to an inverse demand function? The main reason is the firm is going to sell its product at the maximum price. And the only way we're going to obtain that maximum price is to transform the direct demand function to an inverse demand function, is to obtain the inverse demand function. And that inverse demand function becomes the maximum price at which the firm is going to sell its product. If he sells his product at that maximum price, then he is going to maximize profit. Now, if we take the derivative of the profit function with respect to quantity, we're going to have the RQ dQ minus the CQ dQ. And that becomes what? Pi prime Q equals R prime Q minus C prime Q. Pi prime Q equals R prime Q minus C prime Q. So this is the condition for profit maximization, which is pi prime Q equals to 0. Remember, pi prime Q is just what? D pi dq, right? So that is to say R prime Q is equals to C prime Q. In other words, R prime Q, which is the marginal revenue, is equals to C prime Q, which is the marginal cost. So for profit to be maximized, the marginal revenue must be equals to the marginal cost. so the firm maximizes profit at that particular level. Now, let's take a look at one exercise here. This exercise is from Stephen Land's book, Price Theory, page 6 to 8. Now, a firm faces the demand function Q equals 100 minus 2P. Now, this is the direct demand function. And the total cost function CQ equals Q squared. Determine the profit maximizing level of output of the firm and the corresponding price of the products it sells. So what is the corresponding price of the product it sells? Now, how do we go about doing this one? We have the direct demand function. Do we need to take this direct demand function, Q, and multiply by the price? Certainly not. This is not the maximum price at which the firm is going to sell the product. So how do we get the maximum price? We get the maximum price by obtaining the inverse demand function, which is what? The maximum price at which the firm is going to sell the product. And that maximum price is a function of the quantity. So what we do here, we transform this demand function to an inverse demand function, and that becomes, if we take the 2p minus 2p to the other side of the equation, it becomes 2p equals to 100, right? 2p equals to 100 minus q, because if we transform the q to the right and then the minus 2p to the left, it becomes 2p equals to 100 minus q. And then if we solve for p, we're going to have 100 over 2 and then q over 2, right? That gives us 50 minus 0.5 q. So p equals to 50 minus 0.5 q, right? The total cost function CQ equals to Q squared. Now, this is the total cost function. So what do we do here? We simply subtract that total cost from the revenue. So let's go ahead and find the revenue. So the first step is what? We obtain the maximum price at which the firm sells the product by deriving the inverse demand function, right? So this is the direct demand function. The inverse of the direct demand function is obtained as what? P equals to 50 minus 0.5 Q, right? Now, after obtaining the inverse demand function, the next step is what? To multiply that by the quantity to get the revenue. That one is straightforward. We multiply that by the quantity and that gives us the revenue, right? So what we do here, when we say price times the quantity, we are going to take that price equation, 50 minus 0.5 Q, and multiply that by Q. That gives us what? Gives us 50 minus Q, right? Multiply by Q, right? We have 50 minus 0.5 Q, and then you multiply everything by Q, right? And that gives us 50Q, right? Minus 0.5 Q squared, right? Right. So that is minus 0.5 Q squared, right there. And which is this one, 50Q minus 0.5 Q squared. The next thing we do is to obtain the profit. How do we obtain the profit? We find the difference between what? The revenue and the cost. So the revenue is RQ and then the cost is CQ. What is the CQ? CQ is just Q squared. We plug in that one. Remember That minus sign affects everything in the cost function, right? So that becomes minus q squared, 50q minus 0.5 q squared minus q squared. Remember, when you say minus 0.5 minus 1 minus q squared is just minus 1.5, right? And that is the profit function. Now, what do we do next? We obtain the profit maximizing level of output by what? Differentiating the profit function with respect to quantity. Divide the Q. And that gives us what? 50. Now remember, simple differentiation. Minus 1.5 Q squared, right? What do we do there? We differentiate this whole function with respect to the quantity. Now remember, the quantity has an exponent which is 1, right? You are going to multiply that exponent by the coefficient of Q, which is 50. And that gives you 50, right? Now, do you need to write 50Q? No. You already have 1, Q raised to the power 1, and then you multiply that coefficient by 50. Then in differentiation, you always have to subtract 1 from the exponent, which is 1 minus 1 is 0. And remember, when you have Q to the 0, it becomes 1, right? So 1 times 50 is 50. So that's how we got the 50. Right? Now this is 1.5. Again, we want to differentiate this minus 1.5 q squared. You multiply that exponent, which is 2, by 1.5, and that gives you what? 3, right? Now what do you do with the 2? Do you leave the 2? Do you leave the 2? Do you leave this 2 or as it is? No, we don't leave the 2 as it is. So what we need to do here is to subtract 1 from that exponent. So remember, when you are differentiating function, you always take 1 from the exponents. That is the independent variable, 1 from the exponent. And then you multiply the exponent first by the coefficient of the variable, right? So if we do that, we have 3q. Remember, 2 minus 1 is 1. What do we need to say? Q to the 1? No, we don't even need to say that, because q to the 1 is just q, right? And what happens? This is equal to what? 0. Now we can simply solve. Now we want to find, now that we have this, right? Let us just try to prove that this is a relative maximum, right? So what do? We just say what? Find the second order derivative, which is what? This square pi. And then the q square, right? Can anybody tell me why we are using this one? We are not using quality here. Can anybody tell me? Okay. The main reason why we are using d here, we are not using quality, is because this function has only one independent variable, right? It has only one independent variable, and that independent variable is quantity, which is q, right? If it has more than 2 variables, it becomes a multivariate function, but this is not a multivariate function. So that is why the derivative, we don't use quality here, okay? There is nothing we hold constant here. You get the point I'm making? So we have d square pi the q square, and that one should be what? Less than 0. It has to be negative. Now this is just by saying, let us find the derivative of the first function, the first derivative. So the first derivative is by the q, and then the second derivative now is to differentiate that first derivative. If we do that, we have 50 minus q, right? And that second order derivative becomes what? Again, you differentiate with respect to q. The power there is what? 1. 1 times minus 3 is minus 3, right? So If it is minus 3, and then q to the 1 minus 1, 1 minus 1 is 0, right? Q to the 0 is 1. So it becomes d squared by the q square, and that is equals to what? That is equals to minus 3. So what happens? This is less than 0, right? Right. It is less than 0. So because it is less than 0, it means profits are maximized. So the sufficient condition is satisfied. Now we have fulfilled the second order derivative. We have fulfilled the sufficient condition. So profits are maximized. So we can go ahead and find our profits maximizing level of output. So how do we go about doing that? We have 50 minus 3q equals to 0. We take 3q to the other side of the equation, it becomes 50 equals to 3q. And then we solve, it becomes what? 50 equals to 3q. Whenever you transpose a term, the sign in front of the term changes. If it were minus, it becomes plus. If it were plus, it becomes minus. Okay? So this becomes a plus here. Now, want to find q, divide by 3. Divide the other side by 3. And if we do that, q becomes what? 16.67. Right? 50 over 3 becomes 16.6. So that is the result. Right? So this becomes the profit maximizing level of output. And it is called Q star. The final step is what? We substitute for the profit function, profit maximizing level of output, into the inverse demand function to obtain obtaining step 1 to obtain the corresponding price. Right? Now you want the corresponding price. How do you do that? Now price is 50 minus 0.5q, right? Already you know what is Q star. It's 16.67. Therefore, the price is obtained as what? P star equals to 50 minus 0.5 Q star. Well, we know Q star is 16.67, right? We just plug that one in there, and then we solve, we have 41.665. So that is the answer. $41.67. $41.67. Okay? So that is the result. So now we have obtained the profit maximizing level of outputs, and then use that one to find the price. Okay. Now let's look at relative minima and relative maxima. What is relative minima? It refers to the point where a graph changes direction from decreasing to increasing. Yes, it starts from decreasing and then it goes to increasing, right? Now, if you look at the relative maxima, it is always, the graph is always U-shaped. For example, we talk about cost curves. We're going to deal with cost curves later on. So in week 3, we're going to deal with cost curves. Now let's look at this function, y equals to ax squared plus bx c squared. And then we have a relative minimum there, which is given as x star and y star. Now, this function has a relative minimum if what? This square, y, the x square is equals to 2a, and that 2 is greater than 0. Then dy, the x is 2x plus b, right? Now, the catch here is we look at the coefficient of x squared. If that one is positive, then it has a minimum. If it is negative, it has a maximum. Okay, that's how we do it. Now, let's say, for example, here we have this polynomial. We want to find the critical value. Remember, when we talk about critical value here, we're talking about what? The optimal values. We want the optimal values. Those are the critical values, right? It's just like saying find the profit maximizing level of output that we just completed. So now those are the critical values, and then you find the maximum profits, or in this case, the relative minimum or maximum, right? Now let's go ahead and solve this problem, this simple problem. If we differentiate the first order condition here, we have 3x squared. That one is self-explanatory, minus 3. I don't even need to do that again. And then we equate the FOC, the first order condition, to 0 and solve for x. dy dx equals to 3x squared minus 3 equals to 0. And now if we equate that, we're going to have 3x squared equals to 3. So if we solve for x there, becomes what? X equals to plus or minus 1, right? Take the 3 to the other side, and then you divide both sides by 3. You get 1. The square root of 1 is just 1, right? So it's plus or minus 1. And the second order condition is what? The y and then the x dx, which is d square y dx square, right? That becomes 6x because 2 times 3 is 6. Then x to the 2 minus 1 is x to the 1, right? Then x to the 1 times 6 is 6x. So we plug in the answer in step 2 to the SOC and determine whether the function has a relative maximum. So we just plug that 1 there. 1, we had 1, right? 1 times 6 is just 6. 6 is positive, right? Okay. So if we plug in minus 1 there, we're going to have a negative. But what happened? In economics, we don't deal with negative values, right? We always deal with positive values. So if at all you have two values, plus or minus 10, always take the plus 10, because in economics, we don't deal with negative numbers. So since the SOC is positive, the function has a relative minimum, and so either cost or expenditure. Now this one should be all. All. It's not O. It's all. Either cost or expenditure is minimized. Now, since the critical value of the function is x equals to 1, we then plug in x equals to 1 into the linear function to get what? Relative minimum. Now, the relative minimum is obtained as what? 3. Right? Now, relative maxima refers to the point where a graph changes direction from increasing to decreasing. This time, it's from increasing to decreasing. Right? Now, if you look at this one, it has a maximum point here, which is the relative maximum. And if you look at this function, it has a minus a instead of a. That tells you that the second order derivative is going to be negative. So this function has what? Relative maximum. Okay? It has a relative minimum if that value a has a positive sign, right? A is positive. A is positive there. But if we have minus a there, it becomes negative. Okay? Oh. Again, everything here is self-explanatory. Now, the condition for cost minimization and profit maximization. I said, for cost minimization is d square d cd, the CQ, the Q, which is 0, and d square c square is positive, right? So we do apply relative maxima and minima in economics, especially in microeconomics, when we talk about optimization. And that is what we're going to be doing throughout in this program, in this particular course, right? Simple, basic math, simple calculus. It is not difficult. I think nobody needs to go to Cambridge to understand this one. You don't even need to go to Cambridge. Just follow the slides and then read the book. You'll be able to do everything. And there is no need for you to panic. And these are very simple stuff, very basic, right? So I expect everybody to know this one. For a given cost function given as CQ equals to f of q, then what is the cost function? Is CQ equals f of q, and then the CQ q equals to 0, which is the first order condition for minimization, second order condition for minimization, is that the second order derivative is positive, right? Right. So for maximization, the conditions are again d pi dq equals to 0 and then d square pi dq square is negative. Now you see, for profit maximization, the second order derivative is negative. And then for cost minimization, it is positive. So as a matter of fact, all the conditions are similar for both profit and cost. The only difference is that for profit maximization, the second order derivative is negative. And then for cost minimization, the second order derivative is positive. Okay? So both the cost minimization condition and profit maximization condition, they have the same first order condition. Okay? So that is the first derivative is equals to 0. Now let's look at this. Let's try to have this. I need you guys to go and look at this. Try to compute the marginal cost. I will just give you a clue here. How do you get the marginal cost and the marginal revenue? The marginal cost, of course, is simple. Just differentiate this whole function, right? The cost function, it becomes what? All you need to do is to say the CQ, right? The Q. That's it. That is it. And that is what? Your MC. That is your MC. Okay? That is your marginal cost. The marginal cost is what? The addition to total cost, right? By adding one more unit of output, okay? Or by producing one extra output. Is the additional cost incurred by the farm when that farm decides to increase production by an extra unit? You understand? That is the marginal cost. It is just the addition to total cost when the farm decides to increase output by one more unit. Okay, so that is the marginal cost here. So, and that is the CDQ, which is equals to what? 3Q square, right? 3 minus 1 is 2, right? Minus, what is 2 times 61.25? Is what? 61.25 is what? Is 1, 2, 2.5, right? And that is Q, right? And then plus what? 158. Sorry, 1528.5. Do you need to say Q here? No, because Q is raised to the power 1. 1 times that coefficient is just 1.5. And then Q to the 1 minus 1. 1 minus 1 is just 0. That's fine. And that is equal to 0. That is the first order condition, right? But we don't need to see equals to 0 here because we want to find the marginal cost. So the marginal cost is just obtained as that one, right? Simple. Now, how do you get the profit function? Profit function is just what? You say pi q, right? Equals to what? Revenue, RQ, right? Minus what? CQ, right? Cost. That is the profit function. But you don't need to leave this like that. You need to plug in these values. You have the cost given, right? Now you have the direct demand function. You need to find the maximum price now. How do you get that? The maximum price is obtained as what? Take that minus 5 PD to the other side, you have 0.5 PD. Or just say 0.5 P, right? 0.5 P. That's it. And that equals to what? 600 Q, right? Minus Q. Minus Q. Right? Minus Q. So you have 0.5 divided by 600 divided by 0.5, then P equals what? 600 over 0.5, which is just 1200, minus what? 1 over 0.5 is what? Is 2, right? 2. That's it. Have you seen? So 600 over 0.5 is just 1200, right? So that's how you got that one. So the 600 minus 1200 minus 2Q becomes the price. Multiply that by Q becomes 1200Q minus 2Q square, right? And that is what you're going to plug in here for your revenue. That revenue minus this cost, you see the profit from. Simple as that. How do you get the revenue? That revenue you obtain is what? The margin revenue is what? The RQ, the Q equals to what? The marginal revenue. So you differentiate the revenue function to obtain that. Then you find the profit, maximize the level of output of the farm, the corresponding optimal price. What is the maximum profits? I expect you guys to be able to do that. Plug the Q star into the profit function to obtain the maximum profit. Okay? So I expect you guys to be able to do this. Make sure you're able to solve this one. Right? Make sure you're able to solve this one for the midterm exam. Okay? Make sure you're able to do it. And then I don't want you to say, oh, I don't understand this one. And study this one properly. Okay? Now let's look at constraint optimization here. Right? Unlike unconstrained optimization, constraint optimization is the analytical tool for making the best choice, taking into consideration any possible restrictions on those choices. So here there are restrictions on the choices, and they call them what? The constraints, right? So for constraint optimization, they have like 3 elements. What are these 3 elements? One, you choose between alternatives, right? For example, choosing right, you have so many options, you choose between them to maximize your satisfaction or utility, or maximize your profits, or minimize the cost, right? So the objective function becomes minimize your expenditure, maximize your GPA score, minimize cost, minimize electricity usage, etc. These are all objective functions subject to some constraints on the choices. Okay. Now, let's look at one typical example here. You have a student at Campbell University who is deciding on which courses he or she should take in order to maximize his GPA and at the same time meet all the requirements of his college major. Now, this consumer is considering how much food or clothing he or she should buy in order to maximize his welfare, given his or her income constraints, right? So you are a student. You try to choose your courses. You always want to have an A. You always want to select a course where you can have an A. But at the same time, it's not only a matter of choosing a course that will give you an A, but choosing a course that will meet the requirements for your college major, right? So that is the constraint we are talking about here. It's not only now you want to choose, because you are not going to choose every courses. Of course, there are so many courses. You may decide to do 301. You may decide not to do Econ 301. You may decide to do Econ. If Econ 302 is gonna give you like maximum, maybe it's gonna maximize your GPA. You're gonna get A in Econ 302. You may decide not to choose Econ 301 because Econ 301 is analytical, it is mathematical. So you may decide not to choose that. You may decide to choose maybe another course, maybe international trade, or you may decide to choose some other course, maybe like statistics, maybe finance, something like that, or entrepreneur, something, or human resource management, as long as that particular course meets the requirements of your major. If you know you are going to get an A there, then you can just do that and get your A, then maximize your GPA. So these are some of the things that the student Campbell is confronted with. So as a consumer also, you want to eat so many things. You want to eat food, you want to spend on clothing, you want to spend your money, on some trips, vacation trips, right? So, but do you have all the resources to do that? Certainly not. You don't have all the resources to do that, so you have to economize, right? So, in so doing, you try to maximize your own welfare, right? You get the best out of everything that you consume. You try to get the best. That is what consumers, everybody, that's what we are doing. I don't want to go and buy something that I don't think is very useful to me. If I'm not a drunkard, if I don't smoke, if I don't drink, as for me, I don't drink alcohol. Now, can I even take my money to go and buy alcohol? No, because it's not useful to me. So I'm going to spend my money on things that I think are useful. Things that are useful to me. Those are the things I'm going to buy, right? So like alcohol becomes a bad to me. It's a bad. It's not a good, right? Because this is something that I don't even like. I don't take. Even if you offer it for free, I'm not going to buy it, right? So it's the same thing like um, like cigarettes. I don't smoke cigarettes. Even if you offer me cigarette for free, I'm not going to take it. It is a bad. It is not a good as far as I'm concerned, right? So now the consumer is going to maximize his satisfaction given his constraint, that is his income constraint. He wants to maximize satisfaction, but the income is not there. It's not there. The income is not there, so maybe he satisfies his satisfaction, right? To maximize satisfaction, sorry. To maximize his satisfaction. So because of that, you know, we say the consumer has to prioritize. That is, buy things that are priority to him at the moment and maybe forgo some others, right? So this constraint here has like 3 elements, right? The choice that the individual has to make between alternatives, and then the objective function, which is what? Either to minimize expenditure or maximize profits. And then the constraints, these are the restrictions imposed on the economic agent in a constraint optimization problem. So the restrictions imposed, like for example, uh, 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 meeting the requirements of maybe your college major, that one could be like a restriction, right? Even though you are making your choices, but at the same time, you have to meet the requirements, right? Then for the consumer, even though you're trying to maximize your satisfaction, but at the same time, you have to make sure you work within your means, so that you don't get broke. Don't go broke. Okay? Now, let's look at this example here. Suppose a consumer has only $50 to spend in a restaurant. That's the only amount you have. And you're planning on choosing a collection of dishes. Oh, I forgot the OF here. I was typing so fast. So, of dishes, right? That gives him the most satisfaction without going broke. If there are three, oh my God, this one should be ARE. Ah, my goodness. If there are three different types of dishes, A, B, and C, each unit of A costs $3, the unit of B costs PB dollars, and each unit of the C costs PC dollars, right? Now they say write the objective function of the consumer, specify the constraint function of the consumer, which of the variables are regarded as exogenous and which are endogenous. Write the constraint optimization problem of this consumer. Oh, so what do we need to do here? Now the consumer has only $50 to spend. Obviously, it's constrained, right? By his income. His income is just $50, but he wants to buy three different dishes, right? So, so here, what are those? What are the constraints here? Huh? The constraint is what? Is what this consumer is going to spend on this thing. Now, is expenditure on each of the goods. Total everything, right? Because if you want to maximize satisfaction, right? He wants to get the maximum of all the three dishes. Yeah, he's going to spend on A, he's going to spend on B, and then spend on C. So if you add all those ones, you're going to have what? The quantity of A times PA, quantity of B times PB, quantity of C times PC, right? And that gives you the total expenditure. In other words, the expenditure on all the three goods, right? And that should be less than or equals to the income, which is M. The income is just what? $50. That is your constraint, right? And then what is your objective function? Objective function is simply to maximize utility. Here, your happiness, maximize your happiness here, your satisfaction, your utility, right? Which is U equals to ABC, something like that. That's it. And then what are the endogenous variables here? Of course, we know what endogenous variables that are determined within the system we're analyzing, and then exogenous variables are variables that are determined outside the system we're analyzing, right? So in this case, the price, these ones are all given. The income is given. You already know it. It is something that is given, right? So all exogenous variables are given. Price, PA, PB, and PC together with M. These are all regarded as the exogenous variables. And then what are the endogenous variables? We don't know them. The quantity of the dishes that is going to buy. We don't know them. Those are the endogenous variables, A, B, and C. These are called endogenous variables. Okay? So, as I said here earlier, you have maximize U ABC equals to ABC. That's it. That's your objective function. And then what's your constraint? The expenditure on the goods must be less than or equals to N. It must be less than or equals to $50. That is your constraint. Okay? Otherwise, you're gonna go broke. Can you spend more than $50? No. So the consumer's choices are just the dishes A, B, and C, and so these are what the individual variables. Budgets, these are budgets of $50 fixed, and so the consumer consider this as given exogenous. Prices are also fixed, and so they are all in the exogenous as well. So this is the optimization problem. Maximize UABC equals to ABC as an equals to. So that is the objective function, right? Make sure you are able to know these things. And I need you to maybe skim through Besanko, Microeconomics by Besanko. You remember the PDF document I sent to you. Make sure you go through that one as well. Read that one side by side with Price Theory Landsberg. Okay, side by side with Landsberg. That book is so easy to read, and everything there is self-explanatory. Read that one side by side. You have all those things that said learning by doing. You know, it helps you greatly. Go through it. There is um, there is not much difficulty with that. Reading that, it is not difficult. It is simple, easy. Even the Landsberg book is also easy to read. And make sure you read them. I know some of you are working. I know some of you have jobs. You have children. Some of you have so many other commitments. But just spend 1 or 2 hours, reading microeconomics. I know most of you have to do so many other courses, but you also need to spend some time reading microeconomics. Okay. So let's move on.